All right, so the first two problems, I go back and look at the directions here, say sketch the graph by hand and compare it with the parent function 1 over x. So you can still graph these first two using all the rules we talked about in the notes, but don't forget about transformations because that can make things easier. So this graph compared to f of x, compared to the parent function 1 over x, has been moved to the right 6 units because of the x minus 6. So where normally, remember, the parent function has x equals 0, y equals 0. So now it would be x equals 6 for the vertical asymptote. And it'd still be y equals 0 because there's no vertical shift for the horizontal asymptote. Normally, the parent function 1 over x had a point at 1, 1. So that's now going to be, move it to the right 6. That's going to be at 8, 1. Oops, 7, 1. I went too far on my vertical asymptote, sorry. Put this correctly at 6. These are 10 by 10 grids. There we go. So, sorry, saying that again. The point that was at 1, 1 should be at 7, 1. That's better. And there was a point at negative 1, 1 on the f of x parent function, so that would be here. And remember, when we sketch rational graphs, you don't need a ton of extra points because you know that the graph should fit into, I kind of say it fits into these corners. Make sure you're not being sloppy and doing this. This would be wrong. The graph does not come back out like that. Asymptotes guide us about end behavior. So the graph should be approaching the asymptotes, whether they're vertical or horizontal. Number 8 has a few more transformations. So right here, this is the same as having a negative out in front of the function. So it's like we had a negative 1 over x, and then we did a plus 2 inside of the function, and then we have a minus 4. So I would say this was an x-axis reflection. And then the graph has been translated to the, oops, not right. Not sure if I said right, left 2 units, and down 4 units. Now the left and down are interchangeable as far as which order you do that in. So again, that means that instead of having this graph with the branches in quadrants 1 and 3, reflecting that across the x, or honestly the y-axis, it's an odd function, so they look the same, should be looking branches in these opposite corners, quadrants 2 and 4, but then we have to shift that left 2 and down 4. So the new vertical asymptote is at x equals negative 2. And the horizontal asymptote, instead of being at 0, it's down at 1, 2, 3, negative 4. And remember, you've got these two branches here. So I kind of just think from the center, because we don't have any sort of stretch here. From the center, I would just plot a point here, plot a point here, or you can think of physically moving the point negative 1, 1, left 2, down 4, and the points, where was it? 1, negative 1, left 2, down 4, that lands you here. And you just sketch in your smooth branches. Try not to cross through the asymptotes and try not to pull the graph away from them either. All right, now the rest of these graphs are not easily done with transformations because we have x's in the numerator, and that kind of messes everything up. So now we go back to relying on the rules that we talked about in the notes today. And I'm just going to list everything out. They just sort of, the directions just sort of say, for this section, as sketching aids, check for intercepts, asymptotes, holes, etc. When we have a quiz, you'll be getting points. I'll have all that listed out. So I'm just going to keep in that practice and start with simplifying first. Can I simplify anything? No. Vertical asymptote is x equals 1. I like to kind of sketch in as I go, so there's that. Horizontal asymptote, this is a tie. Y equals negative 3 over negative 1. Y equals 3. So I like sketching in the asymptotes first to give myself some boundaries here. And then we want to do x and y intercepts if they exist because that gets you some points on the graph. So let's start with x-intercepts. Doesn't matter really. Remember, x-intercept is when you're setting p of x equal to 0. And that, when you're talking about a fraction, we did this in the notes over and over. The first step would be you're solving a rational equation, multiply the denominator out of there. So it's really just when is 1 minus 3x equal to 0? So you can kind of think of it as just set the numerator equal to 0 each time. Add 3x, divide by 3. So x equals 1/3. So that's about here, right? And then a y-intercept is finding p of 0. If you plug in 0 for x, you get 1 over 1. So the point 0, 1 is an intercept. So I have 2 points on the graph, but they happen to be on the same branch. So not super helpful as far as the other branch goes. So I'm not sure why I extended this all the way out like this. I made that branch extra long. That may not be as accurate as it should be with some of these other points, but you don't have to plot extra points. For this branch anyway, I will find p of 2 to see where that lands. It's 1 minus 6 over 1 minus 2. 1 minus 6 is negative 5 over negative 1, which is positive 5. So 2, 5 is right here. And then I'll just sketch this branch in. All right, number 22. Same idea. Start with vertical asymptote. Oh, actually, no. Before you start with vertical asymptotes, I can't just say this is left 2 up 2 because there's an x up here. So if this were a 1, it'd be an easy transformation graph. Because it's not, you do need to get a common denominator. So the 2 is going to get multiplied by x plus 2, 2x plus 4, all over x plus 2. We do need to get this into a common denominator, into one single fraction for all of our rules to work as far as horizontal asymptote rules, vertical asymptote, all of that stuff. So this is really the function that I'm looking at. It's equivalent. It's the same thing. I've just combined it into one. Okay, so vertical asymptote, there's one at negative 2. Horizontal asymptote, so this is where you would say like, oh, it's a tie, y equals 1 if you don't do this work. But actually, it is a tie, true, but y equals 3 over 1. So y equals 3. It is important if you don't see a single fraction to get that fraction together, with the exception of something like g of x. This one I was allowed to leave alone because that wasn't an x up there, it was just a number. But if it's easier for you, I could have done a common denominator here and followed all the rules. All right, x-intercept. When is 3x plus 4 equal to 0? When x equals negative 4/3. That's negative 1 and 1/3. And then y-intercept, plug in 0, and you get 4 over 2, which is 2. So 0, 2. All right, so we have the branch on the right. Now I'll just do one extra point. I need to be on the left side of the vertical asymptote, so I'm going to find g of negative 3. Plugging into my rearranged version here, so that's negative 9 plus 4 over negative 3 plus 2. Negative 5 over negative 1 is 5, so negative 3, 5. It's right here. I would like you to plot 1 point accurately on each graph. So you may be saying, like, there are patterns to figure out if the two branches will be in opposite quadrants or the same one, like if there's quantity squared or whatever. So if you're paying attention to some of those patterns, I don't usually bother with them. I still want you to plot 1 accurate point. So even if you know the branch is going to be up here, don't just sketch it in. I want you to have 1 point plotted because it's not that hard to plug in 1 point, and it brings our accuracy points up just a little bit. All right, next one. Remember, this can be t squared over 3 plus t, 3 minus t. And that's important for vertical asymptotes. You want to make sure you're not missing one. T is equal to plus or minus 3, not just 3. So I'm going to sketch these in. For the horizontal asymptote, this is a tie. 1 divided by -1 is y equals -1. So we have sort of this, I look at this as like an H. So we're going to have 3 branches, something in the middle and some on the far left, something on the far right. The x-intercept, or I guess the t-intercept in this case, is when the numerator t squared equals 0, because that's when g of t equals 0. So 0 is an x-intercept. 0 is also a y-intercept then, right? I guess I could still say x-intercept, whatever. It doesn't matter. Y-intercept is g of 0, which is also 0. Okay. Now, I kind of know, because even though we're allowed to cross through horizontal asymptotes, that really only happens if the horizontal asymptote is on y equals 0. So I do know this graph is going to open up. But if you're not sure, or if you're just trying to be extra careful, maybe it's test or quiz day or something, it is pretty easy to plug in like g of 1. You get 1 over 9 minus 1. That's 1/8. That's positive is the important part there. And you should know that this is an even function, or you should quickly recognize like, oh yeah, if I plug in -1, I'm going to get the same thing because I'm squaring it. So even if you do take the time to find a couple of points in there, it's not really that time consuming. So there's the middle branch. And then what about the far left and far right branches? So I'm going to say g of 1, 2, 3. I'm just going to do g of 4 for the far right. 16 over 9 minus 16 is 16 over negative, 7? Which is -2 and 2/7. For accuracy's sake, I just want to make sure I place it between the correct 2 integers. So when I go 4 to the right, I'm at -2 and 2/7. So if I were grading you on a test, I would just be looking that you plotted a point somewhere between -2 and -3. Mine's a bit low, but again, that's about as accurate as we can be. And you're also going to want to do g of -4, but that's going to be the same thing, right? Because you're going to square -4 and still get 16 in both instances. So you can go -4 down 2 and 2/7 and have the same thing. This is an even function, so it's got this nice y-axis symmetry. All right. Number 26. So h of x is already factored out for us. That's kind of nice. The vertical asymptotes are x equals 0 and 3. So let's get those in there. 0 and 3. The horizontal asymptote, this, if you were to distribute this together, you'd have 2x plus 4, x squared minus 3x. So this is bottom heavy, which means y equals 0. Just because we have a y equals 0 horizontal asymptote does not mean we can't have x-intercepts. Remember, horizontal asymptotes aren't giving us undefined values. They're just giving us end behavior values. What does this thing keep dividing at, getting very close to if you divide it out for very large or very small values of x? So with that said, there is an x-intercept. It's at x equals -2, right? Because x plus 2 would be equal to 0. So I'm going to plot that point. And then what about a y-intercept? Now, if we have a vertical asymptote at x equals 0, we can't have a y-intercept, right? Because if you plug in 0, you get 2 times 2 over 0 times -3. A non-zero over a 0 is undefined. Okay, so there's no y-intercept, which makes sense. What do I do with this one point? How do I know which way it goes? I might need to do more than one. I definitely need to do more than one extra point over here to figure out what's going on. So I want to know, to the right of this point, does it go down or up? So let's find h of -1. H of -1 is 2 times 1 over -1 times -4. That's 2 over 4. So -1, +1/2. I know the graph doesn't dip back down after this because there are no other x-intercepts. So I know to the right of this point, the graph goes up And because it has a vertical asymptote, it will continue to get closer to that. It's really, I can't leave my graph like that. That was a very rough sketch. That's not much better. And then what about here? It's probably going to dip down a little bit and get back close to the asymptote, but let's see. If we do h of, let's do -3, 2 times -1 over -3 times -6. That's -2 over +18, which is -1/9. So like really negative here. Now you can keep plugging in points if you want. You're probably going to see, well, you're getting closer and closer to 0. Maybe there's a bit more of a dip down here and then it comes back to 0. But all that is to say is that you've got some negative values in here, and then the graph will, in the long run, when you start plugging in like -1 million, -100 million, etc., you're going to be getting something very close to 0. Okay, and then in the middle, we need to know what's happening. So let's find h of 1. That's 2 times 3 over 1 times -2. That's -3. So 1, -3. I do not need to find h of 2. I mean, I could if I want to like be kind of accurate here, but so I guess I just will because I do, but hold on. I'll explain why I didn't necessarily have to do this. So for accuracy's sake, knowing that this dips down here, fine. But if I weren't plotting that, I would have just done some sort of little like parabola type shape anyway. I know this graph doesn't go up because then I would be creating more x-intercepts, and there are no more x-intercepts besides just this one value. So this graph has to stay negative on both sides. Okay, so if you didn't plot that point, you would just still sketch something similar to this. I wouldn't go higher. I would just make it look like kind of a narrow parabola, I guess. And then finally, h of 4, because we need to know if the last branch is above or below the x-axis. When you plug in 4, you get 2 times 6 over 4 times 1. 2 over 4 is 2. 6 over 2 is 3. So 4, 3. Again, I know that this graph does not go cross through the x-axis again because that would generate a new x-intercept, which doesn't exist. So I will just sketch a nice branch in the right side there. All right, 32. I always like these graphs because, first of all, this one finally simplifies. We got to one where something cancels, but these are actually really easy to sketch. Now, this graph is top heavy by degree 1, so we might say like, oh, there's a slant asymptote, but remember to simplify before you get into finding asymptotes. The x minus 4's cancel. So really, this graph, it's not that it is linear, but it looks linear. It looks like the graph y equals x plus 4, but it's going to have a hole in the graph. Okay, so is that linear? No, because linear functions don't have holes, but it looks linear. So that makes this really easy to graph, and I don't have to find all the other stuff. There is no vertical asymptote. There is no horizontal asymptote. I don't have to find a slant asymptote. It would be x plus 4 if I tried to find it, but I don't need to because the graph is on the slant asymptote. There's no point in sketching that in. Okay, so beginning of the year, how do we graph y equals x plus 4? There's a 1, 2, 3. At 0, you get 4. You've got a slope of 1. The only caveat here is at 4, remember there's a hole, at x equals 4, and then you plug that in to your simplified function. So when you get to 4, you've got to do a hole at 8. Otherwise, you've got a nice little line. So everywhere else, this graph exists except for that one hole right there. All right, and then my last two are on the next page in the book here. It says, sketch the graph of the rational function by hand. Now, these two, well, for these 4 evens last night, we already found the slant asymptotes. So I'll kind of refer to that work. But now we're just going to graph these two. So 48 was this. We have a vertical asymptote at x equals 0. I'm sketching that in. Okay, and then from last night's homework, let me find that homework from last night. We did the long division for 48. So I'm just trying to save time on my video here. So we already have this. If you forget how we got that, then practice it again. It was long division. Y equals negative x is the slant asymptote. And I know there's a slant asymptote because this is top heavy by degree 1, and it didn't simplify like 32 did. So y equals negative x means 0, 0, and then you're doing a negative slope, which is down 1, right 1. And remember with slant asymptotes, because they guide the end behavior and you've got to know which side of that line you're on for the branches, it's good to use your tick marks every 1 unit. Okay, what about x-intercepts? When 1 minus x squared is equal to 0, we should get plus or minus 1. That is always great because that actually gives you 2 points on either side of the vertical asymptote, and you don't need any extra points to figure out where the 2 branches are. We talked about this in the notes. For these graphs, either the branches are on the insides, or in this case, they're on the outsides. It's not going to be an inside and an outside combination, because then that wouldn't pass the vertical line test, and it wouldn't be a function. So I'm just going to sketch these in. There's no y-intercept, because you can't plug in 0 for x. So that's it for 48. And our last one is number 50. Again, we did the slant asymptote work on last night's homework for number 50. So I'm going to show you that here. If you need practice with that, do long division again and see that it comes out to y equals x. Okay, so vertical asymptote first. What? Can't write right now. Okay, vertical asymptote first. The denominator is x plus 1, x minus 1. So the vertical asymptotes are at plus or minus 1. That's a bit of a narrow graph if I keep my scale. Don't usually bother changing units. I probably should on this one. There's no horizontal asymptote because it's top heavy. Since it's degree 1 top heavy, and this doesn't simplify, we did long division, got y equals x. And that was on last night's homework. So if you did not understand how I got that, and you haven't had a chance to talk with me about it, please come to office hours. We can go over long division to figure out that asymptote. What about x-intercepts? That's setting the numerator equal to 0. You're allowed to have a point on a slant asymptote. Remember, horizontal asymptotes, slant asymptotes, it's going to be an x-intercept that is on the asymptote if you have a point going through it. And that's okay, because this is not where the graph is undefined. It's just what the graph, it gives you the value that the graph keeps dividing out to as you get larger and larger values of x, or really negative values of x. The y-intercept is the same. If you plug in 0, you get 0. Okay, how do I know if this goes down or up from the center? I don't, so I just have to plug in a point. It's going to have to be a fraction. And again, I really just care about the positive here. So kind of like when we did these rational inequalities, I don't really care about the number value because how accurate do I expect you to be? You're just going 1 point to the right or to the left. So if I plug in 1/2, I get positive 1/8 on top, and then 1/4 minus 1. So it's not that it's hard to do 1/8 divided by negative 3/4, but it's just the fact that it's a positive over a negative is a negative. I mean, as far as accuracy goes, if I'm just asking you to sketch this graph, what do I really care if you compare your line to my line? How different could they possibly be? Okay, so then what if I do negative 1/2? Well, then I'd get negative 1/2 cubed. I'd still get 1/4 minus 1. So now I would get negative 1/8 over negative 3/4, and that is positive. So up and to the left. Again, if we lay our graphs on top of each other, if you actually plot the correct point, the correct numerical value, I think we ought to be pretty close. Okay, we do need to find the points beyond, to the far left and to the far right. So let's find f of negative 2. That gives me negative 8 over 4 minus 1. Negative 8/3 is negative 2 2/3. So negative 2, and then go down 2 2/3. So that's important. You're just below that line because I know that this line goes through exactly at negative 2. So that's where being accurate for your slant asymptote makes a difference. The rest of that curve has to fit nicely into that little corner. And I do know that the other curve will be up in this little corner too, but I'm just going to confirm. I want you to have one accurate point here. It'll just be 8/3, right? Because you're just plugging in 2 instead of negative 2. So 2 and then 1, 2 2/3 is like here. Ooh, I got a little wobbly on my line there, but yeah, that should not be like that. You get the idea. All right, we will practice graphing some more tomorrow. So if you have questions, you can come to office hours, or we have a work day where we can just practice graphing as well.